Well, it's great to continue on part 3 here today. So I'm going to continue to tell you something about this 2D JT gravity, and I'm going to add some simple additional ingredients to it and see how that changes the story a little bit. But before I get to that, I want to very briefly, because it's a long topic, and I don't want to spend the whole time just telling you about this, review the Euclidean analysis of JT gravity where you sum over topologies that was done by SSS. So I just want to very briefly describe how that worked. So the idea is that if we think about the same theory that we mostly discussed in Lorentz signature last time, if we think about the same theory in Euclidean signature, now it looks like if we want to compute something like the thermal partition function, well, we call it the thermal partition function, but we're a thing where the boundary is a circle. Then in addition to diagrams like the disk, which will be related to the usual black hole counting, we might also add things with some handles. And because in this theory, the metric has constant negative curvature, the kind of handles are a very particular shape. So the piece that connects to the nearly ADS2 boundary always takes the form of a kind of trumpet with constant negative curvature. And then we can imagine gluing along a geodesic cut here, the small end of the trumpet, which has some length b, to something else. Some constant negative curvature hyperbolic manifold, Riemann surface that might have several handles. It's supposed to be a picture of a handle. I'm sorry, it's not very nice looking. And in addition, if we computed something like two products, the product of what you would think is the partition function of a dual quantum mechanics, if we thought it was holographic. So we might think of this thing as computing z of beta 1 times z of beta 2. Well, in the Euclidean theory, there are non-factorizing contributions, which, for example, look like a kind of double trumpet. And it was a very beautiful story of Sad, Shanker, and Stanford, how the sum, so that first of all, in this gravity theory, there are finite dimensional moduli spaces of these Riemann surfaces with constant negative curvature. And then there's the infinite dimensional path integral of the boundary wiggles, but that part can be done exactly. And it's also sort of universal and decoupled from the integral over these moduli because this kind of boundary is always geodesically separable from the rest of the stuff. So you can see that in a very simple way. Imagine we start near this nearly ADS2 boundary with a curve. To find a geodesic means to find a curve with minimum length. It will always be a geodesic with minimum length, and you have to reach that place before you hit any topology, right? Because by definition, it's continuously deformable to this outer boundary. So there always has to be a piece that looks like this trumpet, and it turns out the geometry here is fixed other than the shape of the boundary wiggles, and so they just did this computation once and for all. So just because there's within the class of closed loops that are continuously deformable to this boundary, there will be one of minimum length. And so you're not allowed, well, don't break it, right? So in other words, without breaking it, imagine you keep decreasing the length, then it will reach someplace, okay? Okay, this is probably not a rigorous argument, but anyway, it's a true fact about these manifolds. Right. That's what I mean. It's a local minimum. I reach a local minimum and I stop. Yeah. And it never degenerates. Okay. Maybe that's not obvious, but anyway, it's true. Okay, so this story has the structure, and then the volumes of these are very complicated and were studied by Mirzakhami, the mathematician, and in this sort of SSS, they put it all together and they find a nice matrix model. So I'm not going to go through this in detail because that would be a long talk about their work. What do they say the answer looks like? So they have a matrix model called the matrix H because it's going to play the role of the Hamiltonian of the system that lives on the boundary, but I integrate over this Hamiltonian. So it's like a disordered system. So the fact that when I compute something here with two boundaries has these non-factorizing contributions means the answer here isn't just the product of z of beta 1 with z of beta 2 as two numbers, but they interpret it as some kind of disorder average of this thing in this matrix ensemble. And so the rule is there's some potential. I'll have a small caveat about that in a second, but just roughly. And then we'll insert a bunch of trace e to the minus beta h's, however many we have. And this, if I do this matrix integral, it's the full computation of JT gravity with boundaries with length beta 1, beta 2, et cetera, summing over everything, both connected and disconnected. Yeah. Right. You should think of the Hamiltonian as the Hamiltonian of the boundary theory, but we do they do this disorder average over it. Okay. So what they showed is if you do this computation in the matrix integral, then it is equal to the JT gravity computation. So if there's one boundary, you have just one trace. So the number of these is the number of boundaries. I don't know, beta n. And this will be the computation where I have a boundary, a nearly 82 boundary with length beta 1 through beta n, and then I connect them in every possible way, both disconnected and connected. And any possible handles, and I do all of the integrals, they claim that, or they showed, really, that this is equal to that. Any question? Okay, now, just to give you a little flavor of how it works, I'll skip this board that nobody can see, I guess, and jump over here. So the most basic ingredients are the disk computation. That's like genus 0 and one boundary in the language of the... So it's well known that matrix models have a have a genus expansion. So we imagine that this is we could start with some n by n matrix, and then the usual tough limit of matrix models is to take n to infinity while scaling some coupling sitting here, keeping... Understand what? Yeah. Mm-hmm. Sure. I mean, I would say an ordinary ADS CFT. I mean, if we were studying n equals 4 super Young mills, but it's hard to see that. Mm-hmm. Okay. Well, that's right. Yeah. I sympathize, but it's well, this is mathematical identity. Okay. Well, right. So, well, I mean, a more physical. I mean, again, it depends on what is the rules of the game, right? But if we were in a situation where we had a single quantum system that was dual to some theory of gravity, then if you computed you had two decoupled ones, it would simply be a product. And this product in certain regimes where people discussed it might have some erratic behavior, and if you did a little explicit averaging, then you get a nice answer which is related to this answer. Okay, so in a single quantum system, which is chaotic, it often happens that, at least in some regimes, things like this are a good approximation to a different quantity, which is an explicitly average version of this. Okay? But this is a bad approximation to this actual quantity in a real quantum system if you don't do a little bit of explicit averaging. So, I mean, I could discuss that in more detail, but yeah. Yeah. Sure. No. Yeah, I mean, the thing which is average is the product of these. Yeah. Okay, I see. Oh, yeah, I see what you're saying. Yeah. Right. That's true. Sure. So this is, well, anyway. Well, the H is this random matrix.
Oh, there is probably some favorite H. If the SSS, we choose some potential.
No. There will be a favorite H in the case where this thing is a delta function that fixes H, right? That's a very strange potential. Okay, well, there could be some, but as long as the H is fluctuating, it still sounds very weird, right?
The favorite H is somehow due to the parameters of this VSSS.
Well, I mean, there's a saddle point solution for this H, okay? And that's associated to, I mean, that's sort of the leading order associated to this disk partition function. It's like the cinch spectral density that I mentioned last time, right? But that's for the specific VSSS. When I pick a different one, I could get a different saddle value, but it will not be localized, right? Unless there's something very crazy about the, I mean, unless it's very different than a normal matrix model, right? Right. Sure, maybe, yeah. Some level, I would say yes. Yeah. I know, yeah. I think so, yeah. Sure. Right, they didn't have these asymptotically ADS2 boundaries, so the new thing was the interpretation of this matrix as the random Hamiltonian for the boundary in particular. Right? Yeah. I mean, maybe I don't think they probably didn't write it in terms of the variable H, so it's probably a different potential, but it might be ultimately equivalent by some change of variables. I'm not sure. Right. And of course, you can, I mean, in this story, you could do something different on the two boundaries in a more macroscopic sense, like we're allowed to consider the betas to be different. Or if you wanted to put here a modified boundary condition from the gravity point of view, then you will be inserting a different operator. So for instance, you could insert an operator that involved, h squared or something, and then that will correspond to a different boundary condition in the gravity language. But the detailed spectrum of the H is somehow magically the same at all of the boundaries, and that's the result that's equal to this gravity partition function, okay? Right, I was about to say that, yeah. So the sort of the two most basic ingredients are the disk answer, which gives this cinch spectral density. That's the saddle point solution of this matrix model with whatever. So the potential V is supposed to be whatever is the potential where this will be the saddle point solution of the matrix model. Because the range of, yeah, this is about what I was just going to say. So because the range of energy is from 0 to infinity, it's a double-scaled matrix model, because in the ordinary 't Hooft scaling, you keep this range text. Okay, so but here you need to send that out to infinity, so it's a double-scaled model, and so actually this potential doesn't really exist as a function. It has, if we undouble scale the model by putting a cutoff on the high energy part of the spectrum, we could write a particular function, but then in the limit, some of the terms will go to infinity and some of the terms will go to 0 on this function. So it's not really a pointwise defined function. It's defined in the sense of this double-scaled limit. Right? No, I mean if this is a Hermitian matrix, and you know that that's the density, it determines this V. Yeah. Oh. I mean, I was assuming that the n scaling was just an overall factor. So if you added 1 over n corrections, of course, they're not determined by just the disk density. The disk density is just the leading answer. But but the simplest choice, anyway, is that you simply put the factor of n here, and then this is an n-independent thing. Well, maybe it's slightly more subtle because it's double-scaled, but if we chose a particular, I mean, if we approach this density with a particular cutoff version, then the cutoff version will be associated to a particular v, and then we take the limit on both sides. Okay? And then the other basic ingredient is that double trumpet. This manifold is characterized by the length of that minimal neck geodesic in there, and it was computed by these folks to be given by the following expression. I'm going to leave out a few numerical factors just because I want to get on to the next thing I want to tell you about. So this factor is sort of the single trumpet, and then you take 2 of them and glue them together. And the choice of measure here for this integration is, in a certain sense, arbitrary. I mean, it's natural from the point of view that there's an angle here, so you could glue them with a twist by an angle, so that's why you multiply, that's why they put the measure b dB. But in principle, it was a bit arbitrary because you can, of course, I can transform all the answers with geodesic boundaries by a factor and put the canceling factor in this integration, and it will not change anything that they could check. Okay, so it's really convention. And then this integral turns out to be very simple, and it gives you plus beta 2. And from this, if this is interpreted as the genus 0 connected contribution in that matrix model with 2 insertions of trace e to the minus beta h, you can do a functional transform to compute instead the connected 2-point function of the resolvent, which is trace of a number minus the matrix, 1 over a number minus the matrix, which is a very typical variable studied in matrix models. We compute this at genus 0 connected. That's just a functional transform if we believe the formula over there. And if you do this functional transform, they found the following expression. Where I assume that where one assumes one sits not in the cut. In other words, you don't want to take e to be a positive real number because otherwise you'll sit directly on the pole. Okay, so e away from the positive real axis, then you'll get this answer. And this is a universal answer in matrix models. It turns out that in any Hermitian matrix model, regardless of the matrix potential, the 2-point function of the resolvent at genus 0, the connected place of the 2-point function, has a form which depends only on the endpoints of the eigenvalue distribution, and if the range is from 0 to infinity, this is the universal answer. So this is independent of the potential v of h. And so that's kind of an important check that the thing looks like a Hermitian matrix integral, not, in other words, this comes only from the Vandermonde determinant. So this is kind of a check of the Vandermonde, and the rest of it also works, okay? Right, this is the double trumpet. Yeah. Well, I just mean that there is an arbitrariness in that in the things that were checked, you never had a free boundary that was ended on a geodesic, right? You always glued them together. And so you're free to say that the measure is anything and then rescale the pants and trumpets by the appropriate inverse factor, right? Right. So in other words, if I didn't put the b here, I could put square root of b here and here. It's just a convention, okay? There's no computation that went into saying that this is BDB. That will be important and something I'm going to tell you about soon. Okay, so that was this story. And there's something about it which is kind of mysterious because we usually thought that, you know, the dual of some theory of gravity is supposed to be single quantum mechanics. Instead, it's this funny rule, right? But that was, yeah, Mark.
My recollection is that in SSS, they derive BDB from BS theory.
I would say no. They made an arbitrary choice. I mean, they made some choice. No. You can't derive it because you can't derive it unless you. What is the meaning of BDB, right? In other words, they never did a computation which had a geodesic that just, you know, they never did a computation where you physically ended the space of the geodesic, right? So there's no invariant meaning to this measure. They always had two pieces glued together, so there's nothing to check, right? They had some particular rule, and from that rule they maybe derived a particular thing, but the input was a convention, and then the output is also a convention, okay? Right, that was sort of the logic, but the thing which is well defined is, for instance. Well, okay, but I mean here it also has the boundary wiggles. What did you want to put here on the ends of this hyperbolic cylinder? So a computation is the thing with these nearly ADS2 boundary conditions at the ends of the hyperbolic cylinder, which they call the double trumpet, and that's a particular answer which they computed correctly. And you can break the answer up into an integral over b, where this sounds sort of natural. This sounds natural because, you know, is the length. Right. So this is supposed to be the integral over the twist. Okay, but that's actually a convention. I mean, nothing tells you. I mean, nothing tells you that. Well, maybe I'll get to it later. Okay. Anyway, this is a correct answer. Sure.
Values and volumes. More derivation. Volumes of respective well-defined volumes.
I agree, but I agree, but soon I'm going to add some end-of-the-world brands. And when you add the end-of-the-world brand, then you can have a configuration that looks like the trumpet, which just ends. And then there is a non-trivial question when you study, say, JT gravity with that boundary condition that cuts the space of the geodesic, what is the integral over b that you get? And it will not be just that, okay? There's some different measure, if you like. But that's not a contradiction, because they didn't study the problem where you ended the space with some particular boundary condition and you compute the determinant with that boundary condition. That's a distinct question. That was the only, that was why I said, maybe I jumped ahead. Okay, anyway, let's worry about that when we come to it in a moment, okay? So again, we have this interesting discrepancy between the thing we would naively have done in Lorentz signature, which was a simple canonical quantization. Yeah.
Can you repeat us? What is the discrepancy?
Discrepancy between what?
You said that there's, can you repeat again what is the discrepancy?
Between the Euclidean and Lorentzian things? Yeah. Oh, yeah, that's exactly what I was saying. So I mean, in Lorentz signatures, there was this simple picture of canonical quantization. You get a Hilbert space whenever I have two ADS boundaries. There's no meaning to the theory with only one boundary because the space has nowhere to end. And it's a perfectly well-defined, non-disordered quantum mechanics with a continuous spectrum. And it seems to have nothing to do with things like the Bekenstein-Hawking entropy. On the other hand, if you do Euclidean analysis and you do the computation with a single ADS2 boundary, the leading contribution looks like the disk, which looks like the Bekenstein-Hawking entropy answer. And then you can compute all of these corrections with handles. And it seems that it's non-factorized in the sense that if I have multiple boundaries, the answer isn't just a product. So it's not like a single quantum system. It's somehow this cumulative, this average where all the boundaries have the same Hamiltonian, but I integrate over this Hamiltonian. So it looks non-local, right? It looks very non-local. Okay, so that's sort of the sort of the discrepancy. Actually, there's this work of Marolf and Maxfield where they gave, in a simplified example, some Lorenzian interpretation of what this integral is doing. And maybe I'll mention it briefly, although I really want to get on to the next thing. But so what they said is, in the Lorentzian theory, you should also allow yourself to consider configurations which have disconnected pieces. So in addition to Lorentzian geometries where the spatial slice looks like this with two ADS boundaries, we can also have just closed circles. Okay, and we can try to study this in Lorentzian JT gravity, and this closed circle might contribute to the Hilbert space of the total thing, and then there can be Euclidean instantons which connect things with different numbers of closed universes, and that looks like some slicing of the picture with the handles. And if you do that in JT gravity, presumably you find that the Hilbert space of these closed universes can be labeled by the choice of the matrix H. Okay, so they didn't actually do that. They studied it in a simplified model, but that's probably how it would work out if you repeated their discussion in the case of JT gravity.
How do you interpret the matrix H?
It's somewhat involved, but so a priori, on a time slice like this, they thought about the states with baby universes in a slightly different way, namely what you could produce by doing a Euclidean path integral with a bunch of boundaries. So I can do a Euclidean path integral. Let's suppose I forget this piece. I just want to construct the Hilbert space of closed universes in this same JT gravity. Well, then they said one way you can do that is you put in a bunch of boundary conditions by hand. They could be any kind of boundary conditions. In particular, they could be the nearly ADS2 ones, but they could be also anything else. And then you do the full path integral, and maybe they're connected pieces and disconnected pieces and different kind of handles and whatever. And then you make a final cut up here, and you'll get some state of closed universes. Okay? And this will have some number of circles, some picture. Okay? But they label the state by this. So they would call this state something like, Z of beta 1, Z of beta 2, etc. And at this point, this is just a name. That's the name of the state. And then the inner product is computed by doing the Euclidean path integral. Okay, and so the idea is these states span the whole Hilbert space of baby universes, but the inner product might make many of them not orthogonal, right? I mean, the states with different betas aren't orthogonal to each other. They have a non-trivial matrix of overlaps. There may be a lot of null states. And if we go back to this formula, suppose you this is going to sound slightly circular, but anyway, the idea would be that we can also act on these states with a computation like this and think about it as an operator. So you can put here another z of beta acting on this state, and that gives you another state. So we can also think of z of beta as operators that act on this, and we can try to ask to diagonalize this operator z of beta in this Hilbert space. But it's clear because of the structure of this answer that the states that would diagonalize it are like the ones which are single instantiation of the h, because then it will make the operator z of beta just be this, which is a number. So it becomes a number when you pick a particular edge. And so in this very indirect way, you will conclude that I can make an orthonormal basis of these things by states labeled by a Hamiltonian, which is drawn from that ensemble. And in principle, every possible Hamiltonian corresponds to one of the states here. But to flesh out every detail in that was never actually done, but they checked this very similar story in a topological gravity, where the data, instead of being a Hamiltonian, was just a number. So it was a bit simpler, but in principle, it should work in this way. I think that would be their conjecture. So this would, in a sense, give a Lorenzian interpretation of what this Euclidean computations do, but in higher dimensions, this story would sound very bizarre, because if we pick one of these particulars, so first of all, this will lead you to an enormous amount of disorder, right? The amount of disorder in H is the dimensionality of the Hilbert space, right? Every eigenvalue can be moved around. If we are in higher dimensions, we don't expect that the theory that would live on, a boundary in ADS3 or higher, which will be a quantum field theory in higher dimensions, not just the quantum mechanics, we don't think that they will come with e to the s parameters. And there's a real distinction between quantum mechanics and field theory in higher dimensions. In quantum mechanics, there are no constraints of locality, right? So any Hamiltonian is good. So in principle, the quantum mechanics, where I just write a Hamiltonian with a bunch of eigenvalues, it's perfectly fine as quantum mechanics. And if we try to do this thing in higher dimensions, we could probably write a more complicated kind of matrix model like this, also including other operators associated to other sources I could turn on, and write some large matrix model of this type, and it will reproduce perhaps answers that are gravity picture. But what it will never obey is crossing of the heavy operators, right? Because you just didn't input that. So that's something that's very distinct in 2D gravity versus higher D gravity. In 2D gravity, there is no notion that the black hole is not associated to a local operator in the dual theory where you can ask whether the black hole operators obey locality, right? It's sort of trivial. It's just because you're in quantum mechanics, right? So there's nothing to check. You can't take two black holes and put them in the same space-time in 1+1 dimensions. This configuration doesn't have any meaning because the black hole looks like this, and there's no other dimensions of space, so you can't put two of them together in the same picture. Okay, so this is for some stupid reason. So quantum mechanics has no constraints, and QFT does, and so this picture sounds reasonable in quantum mechanics, but it doesn't sound like a good model for what happens in higher dimensions. Okay, this is a little bit of an aside, but I might come back to a point related to that in a little bit.
What was that state H again?
Well, I mean, so I glossed this a little bit, but of course, but the idea was we can think of Z of beta as an operator acting on this Hilbert space of closed universes. We imagine we diagonalize it. That means that in the states where it's diagonal, then Z of beta is a definite number without disorder. Since the computations were equal to this computation, it corresponds to picking a particular edge. Oh, you mean how does this act like an operator? Oh, I mean, you just glue it in, right? I mean, we have a state of closed universes, whatever it is, something like this, and then we have one of these nearly ADS2 boundaries, and it connects into this space in some way, and then you sum everything, and you make another cut here, and you get whatever you get.
The rotation just means that you move zero beta inside.
Yep, it just pulls inside here. So it's very simple, yeah. That's it. No, but I mean, in local Q of T, you don't sum over topologies, right? Sure, but then you don't have a natural action on it of the partition function on another S1, right? What does that mean? Oh, I see what you mean, of course. But it doesn't, I mean, that's true, but the structure is very different because here you sum over all ways of joining them, right? Whereas there you fix the way to join it, and the map you get depends on how you said you joined it, right? So
It depends on the metric.
well, even if it was a topological, even if it was a TQ of T, you are supposed to specify how you glue it, not sum over how you glue it, and that makes the whole difference, right? In other words, I can take some TQ of T, have this Hilbert space on the circle, and say I have another circle here and glue it in like this, and I will produce another state on the circle. That's fine, but I had to tell you that I glued it with this pants. If I glued it like this, I will get a different state on the circle, namely that will be the identity map, right? So, and if I have many of them, it makes a big difference. Right? Okay, so that's why this works in this different way. Okay. Well, so this picture in the JT case is not maybe. Well, anyway, I don't want to go too far down that rabbit hole, but right. So, are there some things we could add to JT gravity to make it a better, a more close analog of what we think happens in higher dimensions? So one thing which is kind of clearly missing in JT gravity is that there aren't, in the Lorentzian analysis, there aren't any single-sided configurations at all, because you have to end your one-dimensional space on a nearly ADS2 boundary, so the only thing you can make are two-sided configurations. Let's try to add to JT gravity some dynamical object that will end space, an end-of-the-world brane, okay? It's a little black holes, but you can't make the black holes out of anything. There aren't any other objects other than the black holes. So what could the microstates of the quantum mechanics, even if it's this disordered thing, what do the individual microstates even mean in the Lorentzian theory? Because there's no way to end the space. So we try to modify the story to make it a little bit more realistic, let's say. Of course, because we're in 1+1 dimensions, the only kind of brane that we can add is a brane that will end space, right? That we can't, because there's only one dimension of space. And these are going to be dynamical objects. Since we want them to be dynamical objects intrinsic to the theory, on the location of this brane, the metric should be allowed to fluctuate. In other words, we should be gauging the diffeomorphisms at the location of this brane. In contrast to an external boundary, like the nearly ADS2 boundary that you add by hand and you fix the metric, this is supposed to be an internal object of the theory. Okay, so we should integrate the metric there. When you have boundary conditions in JT gravity, there's also a choice of whether you want to fix the dilaton or its sort of canonical pair. One could consider both of those as intrinsic objects in principle, but the simpler one is where we also allow the dilaton to fluctuate. That might seem natural from the point of view of the dilaton being a metric modulus of some higher dimensional theory that we got from which we got JT by compactification, so we should let also the dilaton fluctuate. So that's just a choice. This is required to consider it an internal object. Whether we fix the dilaton or its conjugate is a choice, but we'll make that choice in this for now. So we'll pick phi to also fluctuate. And that means that the extrinsic curvature gets fixed. Okay, those are kind of the canonically dual pairs. So the metric is roughly conjugate to the normal derivative of the dilaton, and the dilaton is roughly conjugate to the extrinsic curvature. Okay, so when we fix these two, when we allow these to fluctuate, it means these will end up getting fixed. How do we do that? Well, we could take the same JT action. The bulk part of the action, remember, was this. And now on the location of the end of the world brane, we're going to add a boundary term of this type where mu is a parameter. Okay, so the induced metric times phi times k is like the Gibbons-Hawking type term. And now we are free to add another piece where we don't put the dilaton, and it just measures the length of the boundary. So this is the kind of the rest mass of this brane, right? If we had a particle, this has a 0 + 1 dimensional world line, and the integral of a mass times the length is like the rest mass of this brane, or the tension of the brane. So we could call this the tension or the rest mass. Those are the same because the brane is 0 + 1 dimensional. Okay. Well, again, if we came from higher dimensions, we might have imagined a slightly more natural boundary action would have been that you would get some tension times the integral of the induced metric times the area of the internal space. That might have seemed more natural from the higher D point of view, but because we're working at the limit where phi naught is much bigger than phi, this really reduces to this term in the nearly ADS approximation. So we kind of imagine that phi naught times the higher D mu is this mu, and then this kind of term would be subleading. Of course, we can also consider a more complicated boundary condition where we add a term like phi gamma also. That would lead to some slightly different physics. So there are lots of things one could consider, and I'm going to just make this choice because it's especially simple. Okay, so we'll ignore that, but this is just some kind of object. And probably it's a good leading approximation. So if we have that boundary action, then the boundary equations of motion, in other words, if n is the normal vector to the boundary, we have this equation, so the boundary is a geodesic. And the normal derivative of the dilaton is fixed to be this parameter mu. Okay. And then one can, again, analyze this theory in canonical quantization. So we can try to look at configurations which have the nearly ADS2 boundary on one side and this end of the world brane on the other side, and it makes some 2D space. Here's our space, and we can try to see what do those solutions look like, first classically, and then we can quantize it. That will be the analog of the Lorenzian analysis in the pure JT theory. And, well, the story is, of course, very similar because the metric still has constant negative curvature. We didn't change anything about that. And all we have to do is, the only thing that's distinct is where will this end of the world brane set. Okay, so it will take one of the geometries we already discussed and end it at the end of the world brane instead of continuing it out to a second ADS boundary. And so if you work through it, I'll just sort of tell you the answer. If we use coordinates which cover global ADS2 in the following coordinate system, yeah, okay. You could think of it like that. I think of it a little bit more as being like the branes that would be the black hole microstates. So it's like putting a, well, okay. Maybe we say Rendell-Sundrum is the same as that. But, you know, it's like if we put a D3 brane in the middle of ADS5 times S5, it's kind of this kind of configuration. And then if you had many of them, you would make a black hole. It turns out in this case, well, let me just tell you what the solutions look like, okay? And then we can discuss what it means and what these things do. So we have that's the metric on it. So this is just the solution we talked about last time, the classical solution in these coordinates. And now all I have to do is tell you where the end of the world sits. And it turns out the geodesic equation and then this constraint on the normal derivative of the dilaton at the location of the brain tells you that it sits at this location. Okay, so that turns out to be a geodesic in this metric. And if mu is positive, which sounds physically more natural, perhaps, positive energy, positive rest mass, end of the world brain, then it is always behind the horizon. So the original solution here was the nearly ADS2 boundary, and then it had these horizons, and the end of the world brain will sit here. Okay. So it always sits behind the horizon. Well, I think I do this in a funny way, but it bends the other way, sorry. Probably bends this way. Anyway, maybe that detail is maybe unimportant, but wait, which way does it bend? Maybe I'm drawing it backwards now. Yeah, I'm drawing it backwards now. No, I drew it right the first time. Yeah, the geodesics go this way. Okay, geodesics go this way. Okay, so if we look at a slice here, it looks like the end of the world brain is behind where the horizon would have been. Okay. So this piece in the classical theory, this piece of the space-time, which was the left wedge of the two-sided ADS black hole, looks exactly identical to how it would look if you didn't have this end of the world brain. Okay, so in the classical theory, if you sit outside the horizon, you don't see anything different. It's an interesting point. That's of course not true in the quantum theory. I mean, even if we studied QFT in this background, then this will probably naturally prepare a different state, which probably at late times will look like the two-sided black hole, but it might look different around t equals 0 if we included quantum fluctuations. And again, we can think about fixing the gauge by taking a time here on the ADS boundary and sending in a geodesic. But now we have to say where that geodesic hits on this side. It's not allowed to specify the time that it hits the end of the world brain because diffeomorphisms are gauged there. But you can specify the angle which it hits because this is a geodesic, and the simplest choice is to take it to be a normal there. So we have some slice like this, which hits here, and it's orthogonal to the geodesic of the end of the world brain. So this is a natural choice of gauge, which again in the Lorenzian theory fixes the gauge, right? There's no ambiguity in picking such a slice when it's orthogonal to this guy, at least in the on-shell solutions. Right. So so this will pick the gauge, fixes the gauge on shell in the Lorenzian theory. And again, the natural variable is like the length of this line. I again have to subtract the background ADS divergence out at that boundary. So I'll write a similar formula to what we had before. Subtract this piece. RC is the cutoff value of the radius again. And one can go through similar manipulations, compute the conjugate momentum. And the Hamiltonian, of course, in terms of the global variables, is the same as before, just related to phi at the horizon, because, again, the solution out here is identical. But now we have to rewrite this in terms of this variable instead of the variable we had in the other situation. And in terms of this thing, we get a Hamiltonian that looks like the Morse potential quantum mechanics. Like that. So actually, in the special case that of a tensionless guy, it would be identical to the Liouville quantum mechanics that we had in the two-sided case, which just differ by a factor of 2 because we have only one copy of the boundary, so we only measure the energy on it once. But in general, we'll get this Morse potential. Now, I said that when mu is positive, the end of the world brane always sits behind the horizon, and classically, if mu is negative, it can sit outside the horizon. Then it looks more like the single D3 brane sitting in the middle of ADS, where you can send signals to it and get them back all from the boundary. That can't happen when mu is positive in the classical theory. There's a sense in which there's a quantum correction to mu that shifts it by a half. And so if you look at this Morse potential quantum mechanics, it has bound states. So it always has a continuum, of course, because the potential is not bound as L goes to infinity. But if mu is negative, then this potential has a dip, and it can have bound states, and has bound states if mu is less than minus a half. And we should think of those bound states as being the associated configurations where we have the naked end of the world brane. Okay? So these are the naked brane configurations, and they only appear when mu is less than minus a half, whereas classically you'd have expected them when mu is less than 0. So there's a small shift. Okay. But I'm mostly going to focus on the case of positive mu, although these negative mu configurations might be interesting, depending on whether we think that it's something that's unphysical about having the negative tension brane. I don't know. Maybe incidentally, well, I see Samson's not in the audience, but he had asked me a question on the first day of a setup where you could produce the black hole from collapse and then discuss the evaporation in a controlled theory. This thing with mu negative exactly gives you such an example. So if I started in a configuration with my nearly ADS2 boundary and this negative mu end of the world brane matter, that is matter that doesn't couple to the dilaton, so it's still constant negative curvature, this theory is still essentially solvable. And then I could throw in external matter. The effect of throwing in this external matter is just to kick the boundary out on an exponentially rising trajectory. Then I will develop a horizon here, and I could completely solve this problem in perturbative, well, like in canonical quantization of JT gravity with this end of the world brane and this matter. And if this is, some CFT or some UV complete matter theory, it will be completely unambiguous, UV finite and solvable, and what the state looks like at very late times will be a black hole formed from collapse with an enormous interior ending on this end of the world brane with various matter and some Hawking radiation out here and some inside, and it will never disappear. Okay? So that would be the analysis there. Seems to... Okay, maybe it's a setup that could be interesting to discuss, but I don't have anything to say about it. That comment was to answer the question from the first slide. All right. So what are we going to do with this theory? So first of all, what's time? Oh, I'm out of time. Oh boy. Okay, well, interesting. Let me, if you don't mind, could I go a few minutes extra? I'll try not to go for too much longer extra. Okay, so with that Morse quantum mechanics is a solved quantum mechanics. It's in textbooks, and the energy eigenfunctions are something that are called Whittaker functions. There's some normalization constant. And then this Whittaker function. Evaluated like this, where k is the square root of the energy. Okay, so those are the eigenfunctions of this quantum mechanics. And again, it has a continuous spectrum. So again, if mu is negative, there are a few bound states, but there's always the continuum. And mu is positive, there's only the continuum. And if we try to take the thermal partition function of this quantum mechanics, of course, we should get a divergence because the spectrum is continuous. We could do this computation via Euclidean methods. I glue the Euclidean propagator together, and it makes a single trumpet. And in this case, actually, there's no gauge ambiguity. So even in this, unlike in the double trumpet, where there was a den twist of the spatial slice geodesic, which led to the divergence here, there's still, for a given point here, there's a unique geodesic that comes here and is orthogonal to the end of the trumpet. So here there's no gauge ambiguity, so it looks more straightforward. But if you try to evaluate this, now here's where we have to get the correct measure for the problem of JT gravity ending with that particular boundary action. You have to fix the gauge in the correct way. In principle, you could do this computation, or you could simply take the propagator as computed from this quantum mechanics and glue it together. And they will agree. And it turns out the answer is an integral over b of the factor that was called the trumpet factor by SSS, which is this Gaussian piece that I wrote before. Now I'm putting all the factors back. Okay, so this Gaussian piece. And then e to the minus mu b, that comes from the boundary action, which has length b. And then there's a piece that comes from the one loop determinant, which looks like 1 over 2 sinh b over 2. Okay, so instead of having b in the numerator, we have 1 over sinh b in the denominator. Okay. This doesn't contradict anything because this is a separate computation. Okay? Yes. Yeah, maybe there's a way to get that. I don't know. But if you just plug in mu equals 0 here, you will find 1 over sinh instead of b. Actually, there's a paper of Douglas and Edward Witten where they computed the double trumpet and other manifolds in a somewhat different way using some index theory. And the measure they wrote is, I think, the same as this measure in this example. But the choice of measure in those computations was really convention. Whereas here, there's a definite answer because we have an actual boundary condition here. We're supposed to do some specific computation. And this diverges as b goes to 0, and that's good because this was the quantum mechanics with continuous spectrum, and it's supposed to diverge. Okay? That has a logarithmic divergence. So it's small b, it goes like integral of b over b near b equals 0. Right. B is integrated here. Yeah. Okay. Now, how should we end this? How should we think about this divergence? Well, from one point of view, it's an IR divergence because it came from the regime where this length is very long. The length of the slice is very long. That's why this quantum mechanics had a continuous spectrum, because the potential is not bound as L goes to infinity. On the other hand, you can also think about it as a divergence that comes because b is very small. Okay, so it's because in the region that's giving a divergence, if we had some heavy matter, the heavy matter will start to contribute only when b is very tiny. And we see that also in the Lorenzian picture. It's because if we had some heavy stuff, it will contribute to the thermal partition function at low temperatures only when it's hugely redshifted by being down an extremely long throw. Okay? And so we should think of this as a bulk UV divergence. And we can imagine, now we can take, if we want to continue to analyze this model, so we could just stop here. But if we want to continue analyzing this model, we'll say that we should think about it as an effective theory. So we say that at long distance, the theory is pure JT with this end of the world brane. But at short distance, maybe there is some other ingredients. They only affect the computations where integrals over b become where b goes to 0. And their role in life is to cancel this logarithmic divergence. Okay, so we're going to take some effective field theory point of view in the bulk. I will even tell you the term in the effective action, which is the UV sensitive term. So I'll explain that, but yeah, but it will take a minute to explain. Actually, maybe I can already say it. Where does the divergence come from? It comes from the small b region. What does the small b configuration look like? It basically looks like a cusp. Okay? Now, a cusp can be interpreted in a different way. We can think of the cusp, instead of as the b goes to 0 limit of the trumpet, we can think of the cusp as the angle goes to 0 limit of something, of a cone, right? Sorry, this is a terrible picture. Let's say we have a hyperbolic cone, and alpha is the total angle, so alpha equals 2 pi is the smooth disk. If we have a cone where alpha goes to 0, it's the same cusp as this. And there were papers of Edward Witten and others who argued that if I studied not JT gravity, but a more general W of phi gravity, where I add a potential for the dilaton to the action, if the potential is of a simple exponential type, basically if W of phi is like e to the minus alpha phi, minus 2 pi minus alpha phi, adding this potential is the same as adding an object, an instanton, which generates a cone of angle alpha and then summing an arbitrary number, summing over such instantons. And so this cusp contribution, okay? And so what this computation says is that if I add these end-of-the-world branes, it generates a logarithmically divergent coefficient in the long-distance effective theory for e to the minus 2 pi phi term in the W of phi potential. And so then you just add a compensating term to start with. Okay, so that's the logic. Why would it be non-relativistic?
Non-relativistic view.
Oh, I see. Yeah, right. That's true. Yeah, you could do the canonical analysis in the W of phi gravities in general, and you'll find some other mechanics that I didn't study in detail. But sure. I mean, but again, somehow there's always something a little funny. I mean, this theory already, it had no problem in the canonical analysis, right? The Hamiltonian was bounded from below. It was the Morse potential. It is bounded from below. It's just the spectrum of states is continuous. Okay, it's an interesting question. Yeah, I'm not. So the suggestion, I think, is that with with that W phi gravity that the canonical analysis would have given you a discrete spectrum. That's intriguing. Okay. Okay, that's a good thought. Somehow we didn't go. Yeah, we didn't really pursue that. That's interesting. Okay, that's possible. That's possible. I mean, it would be a lot harder to do the analysis, right? Because once you have this W phi gravity, the metric doesn't have constant negative curvature. But I guess one can still find the classical solutions and try to quantize them.
Well, the intuition being that JT is like the BF theory.
Right. Yeah, okay. Yeah, okay, yeah. Okay. Okay, that's very interesting. Okay, that's possible, yeah. Let's see, maybe I should stop for today given the time? I think it's a good idea. I guess I'll just continue tomorrow, yeah.